Hi, all. So this is lecture 21 of MA 221, the Calc 2 course. So today I'll be talking about the power series. Okay. So a power series in X is a series of the type summation summation Cn x to the n, where n starts from 0 and goes to infinity, which is nothing but C0 plus C1x plus C2x square plus so on, where the Cn's are constants, which is also called the coefficients, and x is a variable. So a typical power series looks like this. One note here, the series may converge for some x and diverge for other values of x. So, you can see that the series completely depends on the value of x, right? So therefore, depending upon the value of x, the series may converge or diverge. Okay. For example, if you consider the geometric series, so summation a n x to the n equal to 0 to infinity, which is like a plus ax plus ax square plus so on, right? So here your common ratio is, I guess, x, right? So each time, so first term is a, then you multiply it with x and get the second term, and then again multiply with x and get the third term, and so on. So the common ratio is x, and this series converge when the common ratio satisfies this inequality. If x is between -1 to 1, then it is converging, and it diverges when your modulus of x is bigger or equal to 1. Okay. In general, a power series centered at C is a series of the form this summation Cn x minus c to the n, and from 0 to infinity, which is nothing but C0 plus C1 x minus c plus C2 x minus c square plus so on. Okay. So basically, when you take this C to be 0, you will get this form of power series. So this should be called power series centered at 0. Okay. Cool. This is an example of a power series. Just a second. Okay. So if my Cn is 1 over n, then my power series centered at 0 with coefficient Cn's 1 over n will look like this, right? X to the n over n. I basically replace Cn with 1 over n there in the example. And that is basically x over 1 plus x squared over 2 plus so on. Okay. The starting term is n equal to 1, so therefore you'll get that. Okay. Now the question is, for which value of x this series converges? So let us try to take some values, some explicit discrete values, and see what happens. If I choose x to be 2, then my series becomes 2 to the n over n, right? And starting from 1 going to infinity. And this diverges, right? You can do the ratio test to conclude it. What if I take x to be half? Then summation n equal to 1 to infinity 1 over 2 to the n times n is a series, and this series converges. Again, you will need to do the ratio test to confirm that. For x equal to 1, my series will be just 1 over n, the famous harmonic series, and we know that this is diverging P series. Okay, if I take x to be -1, then my series becomes -1 to the n over n equal to 1 to infinity. This is again converging. You need to do the alternating series test. And when x equal to 0, then I'll get nothing but 0 n equal to 1 to infinity. And this is 0. So again, this is converging. Okay. So our primary guess is whenever x is between, say, -1 to 1, then probably the series will converge. Why? Because I know that at 1, the series diverges, right? From this line. But at -1, the series converges. So -1 should be included. 1 should not be included in the interval. And our primary case is in between the -1 and 1 for each x, it should converge. The series should converge. So if I move to the next thing, so the series summation Cn x minus c to the n, this will again converge for some interval centered at c of radius r. This is called the interval of convergence. So basically, what this is saying is, say you have a series like this, okay? Then what is interval of convergence? So you can see that C is the center here. C is the center for this series. So say C is here in the number line. Then you will find an R. If you take C minus R and then C plus R, then we'll see soon that in this interval, for every series, there is such an R for which I'll get this interval. And for any X inside this interval, the series will converge. So that's why this is called the interval of convergence. Okay. So interval of convergence. So this will converge when x minus c is less than r, diverge when x minus c is bigger than r. And for the endpoints, which is just x minus c is plus or minus r, we don't know. We have to check explicitly for different problems. And also, let me write here, r is called the radius of convergence. So far, what we have seen, a general series centered, a general power series centered at C will look like this, okay? And for each of these series, we will find an R, which will be called the radius of convergence. And if I take around C, if I take the interval C minus R to C plus R, then that will be called our interval of convergence. Why? Because in that interval, if I choose any X from that interval, then the series will converge with respect to that particular X. Okay. I hope things are making a little bit sense. Okay, let me move on. Okay, so there are three possibilities when we try to evaluate the radius of convergence for a particular series. R might be finite. Then the series converges absolutely on x minus c less than r and diverges when x minus c is bigger than r. And also the endpoints of this interval. So this is basically an interval, right? X lying between c minus r to c plus r. Okay. So for the endpoints, that means for the points c minus r and c plus r, we have to check those the convergence or divergence of those points separately. Okay, the second scenario might be when r is plus infinity. Then the series converges for all values of x. And the third scenario is when r is 0. Then the series converges only when x equal to c. Okay, because for the point x equal to c, the series is nothing but 0, right? It's the 0 series. And that should always converge. Okay, let us move into some examples. So the question is basically you have to find the interval of convergence for this particular power series x to the n over n to the n. So just like the problems of ratio test, I'll take an to be the term of the series, and then an plus 1 will be just replacing n, all the n's with n plus 1, and do the ratio test. So limit n tends to infinity, an plus 1 over an. This will be nothing but limit n tends to infinity. So if you do the calculation, I'm leaving that step because I have already done those in solving the ratio test problems. Then you will get something like this. And then this is nothing but, this should be modulus. So modulus x over 2 times 1 plus 0. And mod x over 2 is the final thing. And then we know that by ratio test, this is diverging when modulus of x over 2 is bigger than 1, right? Remember the statement of ratio test. If the limit of the ratio an plus 1 over an is bigger than 1, then the series diverges. In other words, here we'll get modulus of x is bigger than 2. So whenever this happens, then the series diverges and converges when modulus of x over 2 is less than 1. In other words, x should be less than 2. And we don't know about the endpoints, right? So this, if I draw the line, then 0 is the like center of this series, this power series, and minus 2 to 2 is the primary range for the interval of convergence. But we don't know about the endpoints. We don't know when modulus of x over 2 is 1, which is just modulus of x is 2. So when modulus of x is 2, x has to be either 2 or minus 2. So we have to check at endpoints. So if I put 2 in the series, then I'll get for x equal to 2, the series will become like 2 to the n over n2 to the n, right? N equal to 1 to infinity. This cancels out, and this is basically a harmonic series. I know this diverges. And for the other endpoint, minus 2, probably you can guess already, it should be converging, right? This is just minus 1 to the n over n. Again, by alternative series test, I'll get this to be converging. So at x equal to minus 2, the series converges. So therefore, my interval of convergence becomes so minus 2 should be included and 2 should be excluded. This is the interval of convergence. Okay, cool. For the next problem, okay, so that's how we actually find the interval of convergence for a particular power series. Now let me solve the next problem where you are given with this spatial series, which is x to the n over n factorial. Okay, and this series is quite important. Um, and the first term 1, I got it from like 0 to the sorry, x to the 0 over 0 factorial. So 0 factorial is basically 1. So that's how I got the first term as 1. Okay, so now similar thing. I will take an to be x to the n over n factorial, the term of the series. And then an plus 1 will be x to the n plus 1 over n plus 1 factorial. Then again, the ratio test. Take limit n tends to infinity modulus of an plus 1 over an. If I do the calculation, I'll get limit n tends to infinity modulus of x over n plus 1. I have skipped one step where you have to like calculate and cancel things to make the expressions a bit simpler. And if I calculate this is basically 0, which is less than 1 always for all x. So therefore, my radius of convergence r is infinity, and the interval is all x, that is minus infinity to infinity. So for every value of x, this power series actually converges. Okay. Next example. Here I have a C centered at the point 2, right? I got it from x minus 2. Okay, so again, the same thing. An, now let me write here, ratio test. Yeah. So for the third example, my an is n times x minus 2 to the n, okay? And am plus 1 is n plus 1 times x minus 2 to the n plus 1. So this can be rewritten as n times 1 plus 1 over n, x minus 2 to the n times x minus 2, just to see how things cancels. And then apply the ratio test again. Limit n tends to infinity, a n plus 1 over a n, modulus of that. And again, by simplifying the expressions, I'll get 1 plus 1 over n times modulus of x minus 2. And taking n to be infinity, this quantity is nothing but modulus of x minus 2. And the ratio test says that the convergence of series depends on x like this. When x minus 2 modulus of that is less than 1, then the series converges. The series diverges when x minus 2 modulus of that is bigger than 1. And we don't know about the endpoints yet. X minus 2 is 1. This means x minus 2 is plus or minus 1. This means x is plus 1 or minus 3, I guess. Let's do 1 and three. Okay, so my primary interval looks like, so 2 is the center, and so this is nothing but x minus 2 is minus 1 to 1, and then I can simplify it further. This will be 1 to 3, so it should be 1, 2, 3. This is my primary interval without the endpoints. So I know that in between this portion, if I choose any x, the series will converge. So for endpoints, if I take my x to be 1, then the series becomes just n times 1 to the n equal to 1 to infinity. This is nothing but summation n, and you can see easily this is diverging. Okay, so let me actually take a page here. Page. Okay, so now I can see that at x equal to 1, the series diverges. For x equal to minus 1, the series becomes like n equal to 1 to infinity, n times minus 1 to the n. Okay, and this is not pretty hard to see that this series also diverges. This is, as modulus of an is not going to 0. Okay, this is using the divergence test. So the interval of convergence of the series summation n times x minus 2 to the n equal to 1 to infinity is just 1 to 3. And the radius of convergence is what? Is 2, right? Okay, cool. How do I get the radius of convergence? Because this length from 1 to 3, this length is 2. So, yeah. Okay, for the next type of examples, the question is basically asking if I have a series summation c and x to the n. I don't know what is cn here, but the information that is given to us is the series converge when x equal to minus 3 and diverge when x equal to 5. And what I can say about the convergence of the following series, where there are like explicit x given. So this is the series when I take x equal to 2, This is the series when I take x equal to -6, and this is the series when I take x equal to -4. Okay, so about 1. So if I try to guess what will be the interval and the what will be the interval and what will be the radius of the convergence for the series C and x to the n, I know that 0 is the center of the series, and I also know that from when x equal to -3, the series converges. So I know that from 0 to -3, for this range, the series converge. Okay, and if the series converges for -3, then it should also converge for +3, right? So this whole thing is inside my interval of convergence. Okay. So how I get the +3 here? Because I know that modulus of x should be less than r. And I know that r is at least modulus of r is at least bigger than 3, right? This information I get from this -3. Okay, this is a little bit subtle point, so try to think about it. But I don't know what happens before and after of -3 and 3. So obviously the series 1 converges, right? Because my x is 2. As x is 2, and -2 is inside the interval of convergence. So 1 is done. For 2, x is -6. Okay. So so one more information that I forgot to tell you, that the series diverges when x equal to +5. So therefore, I know that the series diverges when I'm beyond 5 and before -5. So I don't know about this. I don't know what happens in this small range. So I do not know, I do not have any information about convergence or divergence inside that. So when I take x to be -6, the series diverges, right? As x equal to -6 outside of interval of convergence. Okay. For the problem 3, when I take x equal to -4, that is in this unknown region, right? Somewhere here. So therefore, we cannot tell if the series converges or diverges. Okay, fine. Okay, for the next problem, so the remark I want to make here is, in most of the cases, when the question is asking to evaluate the radius of convergence or the interval of convergence, we basically use ratio test, but sometimes it is more convenient to use the root test. So as you can see in this example, if I take an to be x to the n over ln n to the n and apply the root test, then I'll get n to the n over n, which is modulus of x over ln n, which tends to 0, which is less than 1 in any for all x. So therefore, the series converges for all x. So for questions about power series where you have to evaluate the radius of convergence or interval of convergence, you use most of the time ratio test, but sometimes you may need to use the root test. That's it. Okay. The next section is about representing functions by power series. So recall that a power series is of this form. Okay. And the question is, can I find a nice looking function fx, which actually is same as the infinite series? Okay. So let me just focus into the simplest example at the beginning. So if I take this series n equal to 0 to infinity x to the n, which is nothing but 1 plus x squared plus so on. Okay. So this is a geometric series and this converges for modulus x less than 1. That we already know, right? But the question is, what function of x does this series represents? Okay, that is the goal, that is the question. So we know that the geometric series, if I consider this sum, then this sum is same as this expression 1 over 1 minus x when my x is in this range. That we already know about from the geometric series lecture. And the goal of this section is basically to obtain power series expansion of other commonly occurring functions. Okay, this is the goal. Okay, things will be a little bit more clear when I do some particular examples. And this is a convention that if there is no mention of a particular power series, then we mean an expansion about 0. Okay. So what it's saying is most of the time the center for the power series is 0. Okay. Let me focus in some of the examples. So the question A, B, and C is asking to, evaluate what will be the corresponding power series for this nicely looking functions. So for the first function, 1 over 1 plus x, I have to find a power series for that. And the main thing that I need to use is this formula of geometric sum. Okay. So to represent in terms of geometric sum, I can write this as like this. Okay. 1 over 1 minus x. And now this is of the form like 1 over 1 minus x. And if I use the formula, then I'll get n equal to 0 to infinity and then minus x to the n, where my modulus of minus x should be less than 1, right? Because now the x here is replaced with minus x. So I have to do the changes accordingly, which is nothing but modulus of x less than 1. But this is just minus 1 to the n, x to the n. So this is a series representation of this function. Okay, sweet. For the next example, I do the same sort of thing. Here I have 1 minus 2x, so the sum will be by the formula, it will be n equal to 0 to infinity, 2x to the n, and the range will be modulus of 2x is less than 1. Or in other words, it will be modulus of x is less than half, and this series is nothing but n equal to 0 to infinity, 2 to the n, x to the n. That's it. For the third one, I have 1 over 1 minus x to the third. And this is summation n equal to 0 to infinity minus x third to the n. Okay, which is summation minus 1 to the n, x to the 3n, n equal to 0 to infinity. and my range of x will be x to the third is less than 1, and this is same as modulus of x is less than 1. Okay, fine. Okay, in the next problem, I have the opposite type of issue. Here I am given with a series here. So for this ABC problem, I have a function and I have to find a series corresponding to it. And for the next one, I have a series, I have to find the function. Okay, you should understand the chronology here. So, okay, I know that fx is this, which is 1 plus x squared over 2 plus x to the third over 3 times 2, so on. What is the first derivative of it? It will be 1 plus, so this will become 0, right? So I'm not writing it. This x, if I do the derivative, it will give me 1, and so on. I'll get I'll get um, x squared over 2, then I'll get x to the third over 3 times 2 plus so on. So this, if you try to look at it carefully, this thing, when I do the derivative, is nothing but the fx again. So I have a function. So this function has a nice property, right? This function has a nice property. When I do the derivative, I'll get back fx again. I'll get back the same function. Do you remember any function of your, like any known function which behaves like this? So this is nothing but fx is a function that doesn't change. And a function which is same as like this is fx is e to the x, right? So e to the x has the same property, but this is my guess. This is only my guess. I don't know if this is true or not. For that, I have to do some calculations. Let me take one more page. Yeah. Okay, so what I know is y, say y is fx, and this is summation x to the n over n factorial, and starting from 0 to infinity. I know that dy dx, when I take the derivative with respect to x, I'll get back y again. That is the property we have seen before. And this is nothing but solving the simplest kind of differential equation. This will be ln y is x plus c. So y would be like a constant times e to the x, something like this. Okay, because I can take this as ln c. I can do that, no problem. But then this becomes e to the x plus ln c, the x times e to the ln c, which is c e to the x. Okay, this sort of thing is like very common in differential equation. If you have not taken any course on that, you might have some difficulty, but yeah, this is very standard thing. Okay, you can look it up further. So, and also I know that when x equal to 0, my y is equal to 1, right? From the very given power series, right? If I choose x to be 0, then all of this term, right, from the second term will be 0, and I'll be left with 1. So from that I can get that c is 1. Okay, if I put this two information back in my equation, I'll get c to be 1, and that implies my y is just e to the x, which is fx. So indeed the series is nothing but e to the x. Okay, so you have got a power series expansion for this function e to the x. Okay, now this is one theorem which is very important, but I'll not prove it because this is out of our scope right now. If I have a function fx to be this, a power series centered at C, and the radius is just R, then the series can be differentiated and integrated term by term. So I have done the differentiation here of the power series term by term, right? Okay. And the derivative of fx will be just the derivative of this. So it'll be an constant as it is, and then n times x minus c to the n minus 1. Okay. And the good thing, or the surprising thing is, this is derivative series. When I take the derivative of fx, it will be again a power series, right? This power series also have the same radius of convergence, which is pretty amazing. Okay. And the same sort of scenario goes when I take the integration as well. If I take the term by term integration, I'll get this expression, right? X minus c to the n plus 1. And then also I have the same radius of convergence. And this is stated here. The interval of convergence stays the same except possibly at endpoint. So it might happen that when with the actual series, the radius of convergence is R, but at endpoints minus R and R, the series diverges. But when I come back here, this might be an inequality like this. Okay. But that is not like too much worry right now. Okay. So far we have identified this series, right? This series is from the formula of geometric sum. And this is we have got from the previous problem where we have like took the derivative and like solved the differential equation. Okay, fine. Now let me solve these two examples to illustrate the theorem. Okay, for the first one, I have 1 over 1 minus x squared. But remember, I have to use either this or that. These two are like my formula to apply in this problem. Okay, so is this familiar somehow? I guess yes. If I take 1 over 1 minus x and derivative of that, what is this? Let me not write this right here. What is this? This is 1 over 1 minus x whole square, and there is minus and minus. So therefore this is an equality, right? If you are not convinced, do it on your own. I will see that the derivative of this 1 over 1 minus x is same as our given function in A. Okay, but I know that 1 over 1 minus x is same as, so dtx is as it is, and this series is nothing but 1 plus x squared, so on, right? When x is between minus 1 to 1. Okay, cool. Now I can do the term by term derivative, right? So if I do the derivative, I'll get 1. So I will get 0 for the first term, 1 for the second term, then 2x, then 3x squared, then 4x to the third, and so on. Okay, can neglect this plus 0 here. So yeah, I have got the series expansion for 1 over 1 minus x whole square by using the geometric sum. Okay. For the second problem, again, I have to relate somehow ln 1 plus x with one of these two problems. There might be a differentiation or integration involved, but that's fine. So I can see that if I take integration over 1 over 1 plus x dx, then that is ln 1 over x. And again, I have the formula for 1 over 1 plus x, right? I can modify this a little bit. So I can write integration 1 over 1 minus x dx. Okay. And then this series will be just 1 minus x plus minus x whole square plus minus x to the third, so on, for minus x to be less than 1, which is x in between -1 to 1. Okay. This is nothing but 1 minus x plus x squared minus x to the third plus x to the 4 minus x to the 5, and so on. This is nothing but the expression for ln 1 plus x when x is -1 to 1. So this is also important, the range. Okay. So I have evaluated the power series expansion of two nicely looking functions, ln1 over ln1 plus x and 1 over 1 minus x squared. Okay, fine. For the next example, I have to find the series centered at x equal to 0 for arc tan x using this expression. Okay, this is quite interesting because this time, okay, so arc tan x is given as 1 over 1 plus x squared dx plus c, right? Okay, for now, I can neglect this c. This will not be an okay, issue. Or what I can do is I can carry out this c all the time. Same thing, doesn't matter. But again, can I somehow relate this with one of the formula that I have given you already? I can do it like this: 1 over 1 minus x, like this. Okay, fine. Now for this modulus of minus x squared less than 1, I can write this as integration summation n equal to 0 to infinity minus x squared to the n dx plus c. This is just the short form for the geometry sum. Okay. So I have written this sort of thing with x replaced with minus x square as this short sum, because I don't want to write the whole thing. And then if I do the integration term by term, that is, I can interchange the sum and the integration like this. Okay, this is the same thing is going on. I'm just integrating term by term. Then what I'll get -1 to the n, and then x to the 2n plus 1 over 2n plus 1. I believe there is some outside, and there is a plus c there. Okay. Now I have to somehow evaluate this c. The c is a like any constant. I want something crisp. So this implies x is less than 1. That's fine. So to evaluate this c, what I'll do is I'll put in x equal to 0 to find c. So if I put x equal to 0, what is arc tan? On the left hand side, I have arc tan 0. On the right hand side, I'll have just when n equal to 0 in this sum, it'll be -1 to the n, 0 to the 2n plus 1 over 2n plus 1, right? Okay. And oh, okay, sorry, my bad. That's why I was confused. So this should be x to the 0 plus 1 over 0 plus 1, right? I'm replacing n with 0. For n equal to 0, I'll get this. And all the rest of the term will have x to the all the other terms has x in it, right? So when I put x equal to 0, all the terms will be cancelled. And but here also I have x to the 1. So this is minus 1 to the 0 times 0 to the 1 over 1. So I have c on the right hand side. On the left hand side, what is arctan of 0, which is 0 again. So my arctan of 0 will be just summation n equal to 0 to infinity minus 1 to the n x to the 2n plus 1 over 2n plus 1. That's it. But this is valid only for modulus of x less than 1. Okay. I am not sure about the endpoints till now. So, okay, for the endpoints, if I put x to be 1, then I'll get summation n equal to 0 to infinity minus 1 to the n minus 1 to the 2n plus 1 over 2n plus 1. Okay. So my claim is using alternating series test, we can conclude. Let me take one more page. We can conclude that at x equal to 1, the series converges. Okay. And also, at the same time, if I put x equal to 1, the series will look like this. Minus 1 to the n, minus 1 to the 2n plus 1 over 2n plus 1, which is 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9, and so on. This is nothing but arctan of 1, right? This is pi over 4. So that's how we know that this kind of weird looking sum, which is pretty hard to evaluate, what is this infinite sum, by using the power series and stuff, we have evaluated that pi by 4 is the value of this series. So this is quite nice. And your homework is to find what about the other endpoint? What about the other endpoint? Oh, I have it's plus 1. That's why. So, okay. Now it makes more sense. What about the other endpoint, x equal to minus 1? So you can figure it out, I believe. Okay. So I can extend the range of the interval a little bit at least. I know that now this interval becomes at least minus 1 to 1. Okay, 1 is also included this time. But you have to like do the same sort of calculations for minus 1 and then see if minus 1 should be included or not. And one thing I forgot to tell you, for this examples also, you can check separately about convergence at those endpoints. So we just make. Okay, for the last example for today, I'll talk about this series. Okay, so this is kind of like not nice looking example, but I can do the same sort of thing. Here also I can take an to be minus 3 to the n, 2x plus 5 to the n, square root n, right? And then take limit n tends to infinity, an plus 1 over an. Okay, so let me a little bit mention it again. So for this two examples, A and B, where I have like just evaluated this primary sort of interval for the convergence, what you should do is you should also like check at endpoints. One and minus one. Okay. Okay, let me come back to the example. Here also do the ratio test. And then you'll get limit n tends to infinity, 3 to the n. Is modulo, so therefore 3 to the n plus 1 times 2x plus 5 to the n plus 1 over square root n plus 1 over 3 to the n, 2x plus 5 to the n over square root n. And if you do a little bit of calculations, you'll get 3 times 2x plus 5 square root n over square root n plus 1. And if I put the n tends to infinity, and then again do the same trick, take square root of n factored out from this, and then you'll get a nice looking expression. And at the end, you'll get the limit with this. So they take square root n factored out. Depends. Okay. So the series converges absolutely when 3 times 2x plus 5 is less than 1, which is 2x plus 5 less than 1/3. And then again, if I do this a little bit more calculation, then 2x plus 5 should be less than minus 1/3 to plus 1/3. And then add minus 5 everywhere. This will be minus 16 over 3 less than 2x less than 14 over 3 minus 14 over 3. And this is minus 8 over 3 minus 7 over 3. X should be in between this. Okay. So now I have to look at endpoints. So for endpoints, when my x is minus 7 over 3, my 2x plus 5 will be 1/3. So the series will be just minus 1 to the, okay, let me see the series again. So 2x plus 5 is just 1/3, okay? So it'll be minus 1 to the n over square root n to infinity. This converges. You can check this easily by alternative series test. And when x is just minus 8 over 3, 2x plus 5 will be minus 1/3. And then the series will be 1 over square root n to infinity. And this diverges by p-test. Okay. So the series, let me just write this as summation a n. Then this summation a n becomes that. Okay, so therefore our interval of convergence becomes, I should include minus 7 over 3. So x strict between minus 8 over 3 and 7 over 3 should be okay. So this is my final interval of convergence. Okay, so that was it for today's lecture. I have tried to give the details about power series that we need to solve the problems in the homework. Okay, and if you have any questions, you are free to email me. Thank you.